Many textbooks or reference books give you only Ka values, and the reason for that is because we can calculate Kb values if we know what the Ka value is. If we look at our reactions, we look at the reaction for the weak acid, we add water, we get H3O plus hydronium plus the anion. And if we look at our anion, the conjugate base, and we add water, we end up with hydroxide and our conjugate acid. Now, if you notice, when we add these reactions together, the conjugate acid cancels, the conjugate base cancels, and what we end up with is the reaction for water. So that means that when we add an acid and its conjugate base reaction, we end up with water, which is Kw. So if we add the reactions together, that means we have to multiply our constants. The A minus, the HA are going to cancel out, and we end up with the equilibrium constant for water. So the relationship between these two constants, the acid dissociation constant and the base, is Kw. So Ka times Kb gives you Kw. Let's find the pH of 0.1 molar sodium formate solution. Its conjugate acid is formic acid, which has a Ka of 1.8 times 10 to the 4th. Let's start by writing our chemical reaction. So we're going to do this as net ionic because the sodium is, anything with sodium is always soluble, so that is going to form just an ion in the solution. So we're going to start with our formate, and again, water doesn't take part in our equilibrium calculations, but we're going to add it just to make our reaction balanced. We get formic acid and our hydroxide. So we write our ice table. We know the concentration of the formate is 0.1 molar. Our initial concentration of the formic acid is 0, and so is the hydroxide. Our change is going to be minus X for the formate, plus X for the formic acid, plus X for the hydroxide, and at equilibrium, again, we just add down the column. All right, so now in order to do our calculations, we're going to have to figure out what our equilibrium constant expression is. Because this is a base, we need our Kb. So Ka times Kb equals Kw. Kw is the constant for water. So if we want to find Kb, it's Kw divided by Ka. Kw is the constant, 1 times 10 to the negative 14th for water. Ka was given to us for the acid, the conjugate acid. So our Kb value is equal to 5.6 times 10 to the negative 11th. All right, so let's do a quick calculation to figure out if we need to use that X or if we can assume that it is small. So we are going to compare the concentration of the base, our initial concentration, to the Kb. So 0.1 compared to 5.6 times 10 to the negative 11. We end up with an answer of 1.7 times 10 to the 9th, which is significantly larger than 1,000. And so we do not need to use the x in our initial concentration. So we're going to leave the x out. So our Kb, again, products over reactants, divided by our formate, our anion. And we can plug in those numbers. So Kb was 5.6 times 10 to the negative 11. And that is equal to x times x divided by 0.1 molar. Okay, so if we want to solve this, we're going to take our Kb value times our initial concentration, and in order to find x, we need to take the square root. So x equals 2.4 times 10 to the minus 6. Now remember, this x is equal to both the formic acid and the sodium and the hydroxide concentration. So we can find the pOH, because this is hydroxide, the negative log of our 2.4 times 10 to the negative 6. So our pOH is 5.62. And how would we find pH then? We know that pH is equal to 14 minus the pOH. Minus 5.62. So our pH is equal to 8.38. Now, does this make sense as an answer? If we think about it, it's a conjugate base of a weak acid, so we do end up with a pH in the basic range, 8.36. All right, so here is one for you to try as a practice, finding what the Ka is of the acid, the conjugate acid of our base. So we're going to set up our table. We can add water in here to make it balanced, but again, it doesn't play a part in our calculations. So we know that our initial concentration is 0.5, or 0.15, sorry. 0 for HA and 0 for OH minus. Now we have to figure out what our change is. And we do have information about this, right? Because we know that the pOH is 5.45. So if we want to find our OH minus concentration, it's equal to 10 to the negative pOH. And so our OH minus concentration It's going to be 10 to the negative 5.45, which equals 3.55 times 10 to the negative 6. And we really only know this to two significant figures because we have 2 decimal places in our POH. So this tells us what our equilibrium concentration is for OH minus. Okay. It also tells us what our HA concentration is. And because this is small, effectively, we have no change in our initial concentration. Just because of significant figures. So now we can figure out and calculate our KB. KB is going to be equal to our products over our reactants, A minus. We can plug these numbers in. So the HA, 3.6 times 10 to the negative 6th for each of our products over 0.15 for our reactants. If we calculate this out, we get 8.39 times 10 to the negative 11th as our KB. We're asked to find Ka. So Ka is equal to Kw divided by Kb. So Kw is 1 times 10 to the negative 14th divided by Kb. And the Ka for our acid would be 1.2 times 10 to the negative 4th.